Hello everyone, welcome back. I've been talking here about aircraft instrument systems, so let's continue on. Looks like we're still dealing with altimeters, so we'll be talking about the altimeter testing. And we're mostly talking about pedostatic testing, and you can see the technician has a bar call box open. When an aircraft is to be operated under IFR, Instrument Flight Rules, an altimeter test must have been performed within the previous 24 months. Title 14 of the CFRs, Part 91, requires this test, as well as tests on the pedostatic system and on the automatic pressure altitude reporting system. The licensed airframe or airframe and power plant mechanic is not qualified to perform the altimeter inspections. Normally you have a mobile technician that has this rather expensive equipment, fully updated and calibrated. Let's see, they're also referring to Part 43, the appendixes of the CFRs, which detail the requirements for these tests. All right, okay, we have reproduced the appendix to Part 43. This is Appendix E. It's mostly talking about the pedostatic system. The altimeter system test is the title of the section. So basically, as you can see yourself, the static pressure system has to make sure it is free from entrapped moisture and restrictions, making sure that the leakage is within tolerance, and if there's a heater, that it's operational, and there's been no alterations or deformations of the airframe surface that would actually affect the atmosphere that's going across the port. Also, I've listed here on the side other things that could be determined wrong with it. So either it's not showing the correct altitude, or there may be scale error, hysteresis, after effect, friction, case leak, and barometric scale error. Different items that you're actually in effect determining. Question: the requirements for testing and inspection of aircraft static pressure systems required by Section 91-411 are contained in they're referring to the appendix answer. So the specific requirements is the appendix to Part 43 that we've already looked at. Yeah, I know it switches from a requirement under Part 91, and it's referring to an appendix under Part 43. So just recognize some disorganization of the CFRs, or the FARs, I should say. Name several of the indication errors that may be found in altimeters. Okay, well, I guess that's that list we had on the side. Usually hysteresis, since that's a word that is not in most of our vocabularies. There wasn't there scale error, a barometric scale error, I believe there was one for case leak, and one I think was called After Effect. Let's see what they say here. Scale errors, hysteresis, friction, and installation errors. Something to review. We've got some text here about altimeter errors. I guess we're talking a little more detail about what is hysteresis error. And I think I'm going to need some sound dampening because I can hear that I've got a bit of an echo. So, and my speakers are off. So I turned down the volume a little bit in the mixer. But this is not the best environment. Not sure why. All right. Well, for your own information, you've probably been reading it on the screen. Hysteresis error. Installation error. And below, mechanical hysteresis and installation summaries. A close-up of the tester. This one here is named pedostat, which is the two items that they're actually testing. You can see pedo on the left and static on the right. Certified pedostatic tester must be used when testing the altimeter and static system as required by FAR Part 91. In addition, the manufacturer or certified repair station must perform these tests. However, a certificated airframe mechanic may test and inspect the static pressure system, but not the altimeter system. I'll have to think about that last statement. Must be a discrepancy in the code. And here's the Barfield tester. It's pretty much standard. And we do have this in the hangar. So pressure and suction must be applied and released slowly to avoid damage to the instruments, which is a good rule of thumb altogether. The method of testing consists of applying pressure and suction to pressure heads and static vents, respectively, using a leak tester and coupling adapters. Similar to having a shop air and a vacuum, both handy, and having special connections to attach it to the aircraft. The rate of leakage should be within the permissible tolerances for the type of aircraft. An unpressurized aircraft system must leak no more than 100 feet in 1 minute with a differential pressure of 1 inches of mercury or an altimeter setting of 1,000 feet above field elevation. So one of the regulations require that you have to at least have that degree of security of your system in order to permit it to be flown, certainly IFR conditions. So that's what, a reading of 100 feet per minute that you're losing. So if you actually are showing on the screen or the dial that your pressure is dropping, and you can see the reading of your altimeter is actually dropping from, say, 4,000 feet down to 3,900 feet in less than a minute, you know you have a leaky system more than likely. You attach the test unit to the other static port, apply vacuum to the static system until the altimeter indicates 1,000 feet above the present altitude. And you're doing that with the handles here. You're in effect pumping the air out. Seal off the unit and let the system set for 1 minute. After 1 minute, you then take your reading. The altimeter must not have dropped more than the 100 feet. If you exceed that limit, you have to locate the leak. To do so, systematically isolate and test portions of the line. Start with the part of the line that is connected to the instruments and work back towards the static ports themselves. Mostly for accessibility, I would imagine, the instruments, and that's where, that's where to start. An air data computer. Many modern turbine aircraft operate at speeds above Mach 0.8. At high speed, pressures build up on the external skin of the aircraft. These pressures cause a distortion of the normal flow of air, causing the pitot-static system to sense false pressures. The system then supplies erroneous information to the flight instruments. The altimeter, for instance, can show an error of more than 3,000 feet. The 3,000-foot error in altitude is intolerable and could put an aircraft in an extremely dangerous position. The ADC was developed to compensate for the errors and display accurate information to the flight crew. So the pitot-static still works. It just needs a flight data computer. Here's some more sophisticated testing equipment. This is testing used on aircraft with the ADC. All right, so when you are using the air data computer in the higher speed aircraft, you can see the outline of the transport category aircraft here with pitot 1, pitot 2, or P1 and 2. I'm sorry, PS and PT. So that you have you don't use your standard tester. Instrument static system leakage. Here, I'm going to take this to the desktop. So static system leakage can be detected by observing the rate of change in indication of the A, airspeed indicator, B, altimeter, C, altimeter. Well, right there, the rate of change for static system, it's going to show up on the altimeter because you're not going to basically have any ram air at that time. So what are the two altimeter choices? Altimeter after pressure has been applied to the static system, or C, altimeter after suction has been applied to the static system. All right, so basically it's a difference between the pressure and the suction, and we were talking about a vacuum or pumping the air out, so that would be C, altimeter after suction has been applied. They're adding a point there that you have to at least trick the altimeter or pump out the air, which will certainly apply the vacuum, and you're tricking the altimeter into thinking that you're at altitude. So you have to be at least 1,000, and apparently it that is the level to test at. So pump it until the altimeter shows you're at 1,000 feet, and let it rip from there. Make your notes. We do have what I call an aircraft in a box. Basically, you open up the box and you have a pitot tube that pops out with the static port, and they can simulate, and they've got an altimeter, so you can simulate the test using those components. The maximum altitude loss permitted during an unpressurized aircraft instrument static pressure system integrity check is, so what were those limits again? All three are asking for 1 minute. So was it 50 feet, 200 feet, or 100 feet? It was 100 feet per minute. Down from 1,000 down to 900 would be unacceptable in a minute. It should hold, ideally, it should hold the full 1,000 for the full minute. I mean, I'm not that crazy about any leakage. Here's a nice little tester. I have yet to throw that together. This looks like I could actually use this. It's kind of like a chicken baster. It's an air bulb that has check valves so that you can just squeeze the air bulb and either, depending on what side you're lined up with, either provide suction or pressure. It's a nice little technician's tool. You can kind of quickly do that. So you don't necessarily need a $10,000 tester. The test can be done with just the aircraft's altimeter and some device to be able to apply pressure and suction. When an unpressurized aircraft static pressure system is leak checked to comply with the requirements of 91.411, what aircraft instrument may be used in lieu of the pitot system tester? I guess I just said it. You don't really need the expensive tester. You can use apply the suction and the vacuum and use the aircraft's altimeter 3. So I'm going to go with C. Another clue is, just I know from writing tests, that if you're going to give two options, you're going to change this to a plural. What aircraft instruments? So if they're saying instrument, they're kind of giving themselves away that it's the only answer that has a single option attached. These questions, they've held up for like a decade, but they are being updated slowly, starting in, well, they started right before the COVID, so I'm not exactly sure whether that was put on hold, but I'll make sure that any of the latest questions I will include, even if I have to include them as an appendix to these presentations. If a static pressure system check reveals excessive leakage, the leaks may be located by, so how do you find the leaks? It drops down in 30 seconds to 900 feet. Where do you think the leak is? Well, it's usually with the testing equipment, but presuming, and you can test your test equipment beforehand by just applying pressure and reading its onboard altimeter. But let's see, pressurizing the system and adding leak detection dye. It sounds pretty messy. B, isolating portions of the line and testing each portion systematically, starting at the aircraft connections. Sounds pretty good to me. Isolating, that basically means you got to be able to put pressure in the first part of the line, and not have it go out the other end. So each let's say you have to put a cap on one of the lines on one end of the line. That is the correct answer. Let's see. Removing and visually inspecting the line segments for leaks. Leaks, obviously, in let's say a rubber hose. Yeah, unlikely for you to visually be able to see those. You already know that, though. About the only tricky part is begin at the instruments. I know sometimes I get a little tricky and add a fourth option, and I might say starting at the static port. Yeah, so don't just presume because you know a little bit of how the right answer goes that somebody might not make a little switch up on that. So understand what you're actually answering. You do start at the instrument. You don't start at the pitot tube or the static port. When performing the static system leakage check as required by section 91.411, the technician utilizes, now they're not really saying pressure or suction. Well, positive pressure is regular pressure, negative pressure is suction, so static pressure. Static pressure is just, you're not changing it. All right, so negative. Oh, I get it. Static pressure because you're checking the static system. That's actually a good loss leader there. I can see where people would think that. Oh, I shouldn't even say it out loud, otherwise you might get that word association. No, just think negative or positive pressure. You're either blowing into something or sucking something out. Rather think of it as a reversible vacuum cleaner. And they have devices in the hangar that can quickly do that. In most hangars, I would presume. Oral question. After components in a pitot-static system have been replaced, what tests or inspections are required? All right, so let's say it's not just up for its 2-year inspection. Say you replace some components. You replace some of the lines, perhaps. Or, maybe the static port itself, became damaged, or the holes became elongated or mutilated. You had to actually replace the static port, which I think may be it's more for example as opposed to whether or not this is actually being done. Well, you're going to have to complete the tests as required by 91.411 as detailed in FAR 43 Appendix E. Which I guess you get a little bit of a hint as to what my background is. Well, this, I would have preferred to have this earlier. We talk about the altimeter itself. That's a nice little, I would like to make this into a project where I have various altimeters with the 3 needles pointing in 3 different directions and having people identify what is the altitude that each one of these are actually reading. You could pretty much follow it just from the illustrations here. What looks like an hour hand is 1,000-foot increments, and that is compared to the minute hand, which is 100-foot increments. So in effect, it's going to go around a full time before the hour hand moves to the next level. And of course, since you're over 10,000 in some cases, you have this third little wand that is usually lingering between 0 and 1 for most flights, most general aviation flights. I guess he gets up higher, but so if you say, okay, this reads 65, that must be 650. But is it 1,650? No, because this hand hasn't gone over there, hasn't gone past the 1,000 or the 10,000 foot mark. Did I say that correctly? That's 10,000 feet. So did I say 650? I guess that's 6,500. So 6,500, but it's not 16,500. They refer to the altimeter that is just sensing the environment as a sensitive altimeter. You'll see that referred to even in some of the questions. For many years, all sensitive altimeters had 3 pointers. The long pointer indicates hundreds. Okay, we went through that. They come in various ranges, up to 80,000 feet, it looks like. There is pilots will adjust their altimeter based on, because altimeters will sense the atmosphere. And if you're normally at 92 or 29.92 inches of mercury on a normal day at a normal temperature, that's the reading. So that's, you wouldn't even really have to set the altimeter. Normally it's already set for that. But if it's the weather conditions change, or the altitude where you're setting off changes, you may already be at some sort of altitude as far as the atmosphere is concerned. So you may have to make some adjustments there so that you can, in effect, compensate for how far off the flat ground you would normally be. The addition of a drum readout for altitude makes it a lot quicker and easier to read. So rather than interpreting any of the dials or the needles or the hands, like the hands of a clock, you can just look at it. It's 1,400. Yeah, very convenient. Encoding altimeters, they're usually in connection with your transponder, your communications with air traffic control. Not only will it take a ping off what your position is, but there's also a code sent which will indicate to the air traffic control what actual altitude you're at. Through the aircraft's transponder. I believe I said that correctly. I may not have. When the transponder replies to an interrogation from air traffic radar, it also sends altitude data. And there's even a more modern version that'll even send more detail to air traffic control. It appears on the ATC's radar screen as a numerical readout next to the radar return for the aircraft. So you'll see a little blip. They'll see a little blip on their screen, but there'll be a little code next to it, a number that'll say what altitude they're at. And like this one here. Well, this one says, okay, 2,019 feet. So that's what is encoded and sent to air traffic control, so they'll know what altitude. So if they get a lot of traffic in one sector, they can also do some vertical guidance. You've seen the operation of a barometer before, just the atmospheric pressure pushes. They originally used mercury to measure pressure and temperature. And so basically, how far up will the regular air pressure push the mercury up the tube? And prevailing atmospheric pressure at ground level, what you're feeling right now more than likely, is 14.7 pounds per square inch, which is also referred to as 29.92 inches of mercury, which is what they're actually demonstrating here. At sea level in a standard atmosphere, the weight of the atmosphere supports a column of mercury 29.92 inches high. You'll see that number a lot, so that's the better one to keep in the memory as opposed to the 14.7. Confusing part is what type of altitude. Sometimes they'll say pressure altitude, absolute altitude, or true altitude. I think absolute, you can basically kind of see what that is. That's how close are you to ground, or even higher terrain, which you certainly don't want to run into that. Pressure altitude is a little trickier. True altitude is what your height is above sea level. So pressure altitude is your height above sea level on a standard day, which would be 29.92, which might be lower than what it is for true altitude. It looks like the actual sea level pressure on that day was 29.7. A little tricky. It's aviation trick questions. Trickier for pilots since they throw the numbers, these designations at them right and left. Mechanics, not as much. We don't have to deal with it as much. We just have to know the basics. When an aircraft altimeter is set at 29.92 inches of mercury, the inch is the little two hash marks, and mercury, the periodic symbol, is Hg. So when you set the altimeter to 29.92, what will the altimeter read? You're on the ground, so what is it going to read? Pressure altitude, density altitude, or field elevation? All right. Well, if you go back to, when they set it for the standard day at 29.92, it read pressure altitude, so that's probably your better answer. It is pressure altitude. Yeah, that's what the altitude reads on a altimeter when you set the barometric scale to standard. So that's a little tricky, so just be aware. I think they may have two questions. Here's the second one. A barometric altimeter indicates pressure altitude when the barometric scale is set at, all right, so it's the reverse of the question. So if it's set at 29.92, what is it? It's pressure altitude. And if it's pressure altitude, what is it set at? 29.92. So the two pressure altitude questions. There's also a radar or radio altimeter, basically the same instrument by two different names. And it's not a sensitive altimeter. It's not reading barometric pressure. It's in effect reading a radio or radar signal that is sent to the ground and it bounces back. So it doesn't really care where sea level is. This mostly tells you feet above ground. It doesn't work real well high, but when you're fairly close to the ground within 2,500 feet, it gives a pretty accurate display. And they call that AGL, above ground level. You'll learn that a little bit more, probably in radar, where talk about radar signals. Radio is the same, but they don't talk about the signals much. They talk about broadcasting and receiving them, but not so much their travel or speed or anything like that, to a certain extent. A radar altimeter determines altitude by A, transmitting a signal and receiving back a reflected signal. Yep. B, receiving signals transmitted from ground radar stations. Or C, means of a transponder interrogation. No, definitely. Should get 100% on that one. A. Basically above ground level. Radar, or in this case, radar altimeter. It's a much shorter version of the same question. It indicates altitude above ground level, AGL, C. Sensitive, I mentioned that already. That's basically your standard altimeter. In this case, it's calibrated for PSI as opposed to. I'm sorry. No, okay. No, it does not work. It's not reading that. It's reading the elevation. I'm sorry, or the altitude. Okay, not much else to say about that. I mentioned it early. We do refer to these as sensitive. They don't send out a radar signal. They basically are sensing the atmosphere and making a calculation, in effect, of how high you are based on the thickness of the atmosphere outside the aircraft. It can also be used to test other pressure-sensitive instruments, such as the manifold pressure gauge, to make sure that it is actually working accordingly. Because there is an oral question that basically says, what aircraft instrument can be used to check the manifold pressure gauge for proper indication? Basically, turn it on, and if it's a prevailing atmospheric pressure is shown without the engine running, the manifold pressure gauge is probably working correctly. Or you can actually use a sensitive altimeter. All right. I am looking to have quick little 5-minute review videos that follow these. This one here has run 38 minutes. And a quick 5-minute review, because I drag it out. But the company that puts out the little review videos, I think it's only going to be about 3 or 4 minutes to review what I just spent 40 minutes talking about. Those same questions. All right, good enough. Thanks for joining me, and as always, see you next time. Goodbye.